This lecture is about the graphs of nonlinear functions. It is a supplemental lecture. You will not be tested on it on the algebra exam. However, many students will find the content helpful for their Harris classes, so I include it here. We'll talk a little bit about the various functional forms, how shifts, addition, and multiplication distort the forms of the graph, and how to recognize the typical set of functions you're likely to encounter in your Harris classes. If you don't think this will be helpful, feel free to skip this lecture. So with that, it's probably helpful to talk about a few types of functions. Obviously, linear functions are of the form y equals mx plus b. Power functions are of the form x raised to a power. Polynomials are linear combinations of power functions. Just for the sake of terminology, we often will say that the order of the polynomial is equal to the highest exponent of that polynomial. So for example, if you had 3x cubed plus 2x minus x plus 1, the order of the polynomial would be third. So that would be a third order polynomial because you had an x cubed. We can talk about rational functions. Rational functions are ratios of polynomials. We can talk about exponential functions, and that we did in great detail in the last lecture, where you have the variable in the exponent itself, and then their inverse logarithmic functions, where you have a logarithm. There are other types of functions like trig functions, but these are the ones that you'll basically be seeing throughout your career at Harris. I want to go back for a moment and think just a little bit about the graphs for lines, because there's some useful concepts here that translate well to nonlinear graphing. You start off by thinking about the line y equals x as a 45-degree line. If you instead have a slope on the line or a coefficient on the x, basically what's happening is you're scaling the line. You're stretching one of the dimensions, which sometimes with linear graphs we think about it rotating the line at the origin by a factor of m. But for other graphs, when you multiply your variable x by a constant, what it will do is it will stretch one of the dimensions of the graph. If you add a constant to your graph, what you do is you shift the graph up by some number of units, by the number of units that you added. The same is true for y equals mx minus b. If b is negative, you're shifting the graph down rather than up. If you add a constant to your variable rather than adding it to the full term of the expression, what happens is it shifts the graph left or right by a units. You can see that with lines pretty clearly. So now we're going to look at, now that we have those concepts of stretching and of shifting graphs, we're going to look at some basic graphs for the different functional forms. So if you have a power function where you have x raised to a particular power, I want you to notice that for positive powers, basically your graph is going to take one of two forms. It will either stay positive, where your y values are always greater than 0, or when x is 0, the y values will be negative. When x is negative, the y values will also be negative, and when x is positive, the y values will also be positive. In fact, you can split that up into even and odd powers. So if you have x squared, for example, or x to the 4th, or x to the 6th, or x to the 8th, basically what you're always going to have is this upward-facing cup shape. Notice that for every single one of these graphs, and it's true for every single power function, you're going to pass through the point 1, 1. And for even positive powers, you're going to pass through the point -1, 1. For odd positive powers, you're always going to start in the lower left quadrant and come in to the upper right quadrant. And notice again, you're passing through the point 1, 1, you're passing through the origin, and the graph is passing through the point -1, -1. Also notice that basically what's happening as the power gets higher is that the curve between 0 and 1 is getting sharper. It's less of a gradual curve. And after x is greater than 1 or x is less than -1, the line goes up much more quickly or goes down much more quickly. And the same is true for the positive powers. Now, if we think about negative powers, basically what we're dealing with there is a special form of a rational function where x to the -8 is the same as 1 over x to the 8. Notice again here, we're still passing through the point 1, 1 and the point 1, -1. But instead of having a cup shape, you will see that the functions are racing up towards positive infinity, towards an asymptote at x equals 0, because these functions are not defined at x equals 0. Notice that as the power becomes larger and larger, the same is true for what we saw with the other power functions, that the turn becomes steeper, and as you go up to infinity, you rise more quickly the larger the power is. With negative powers, basically you're seeing the same sorts of graphs. It's just that what had been above the x-axis on the left-hand side is now flipped below the x-axis on the left-hand side. So really what's going on here is you can think about there being axes of rotation or of reflection for the graph. So in this case, what's going on in the top right corner is basically a 180-degree rotation of what's appearing in the bottom left quarter. Notice again, these odd negative powers are still passing through 1, 1 and passing through -1, -1. Now, if you have a fractional power or a root, your graph is going to look a little bit different. Notice that all of the fractional powers, all of the root functions, remain in the top right quadrant. They all pass through 1, 1. The first one you see here is the square root of x. Notice it starts at 0, 0 and sort of makes a sideways curve up. What's really going on here is this is a parabola like y equals x squared, just rotated 90 degrees, and since we want it to be a function, not including the bottom half of the parabola. As we go to higher order functions, you can imagine that this is basically half of the graph of x to the 5th rotated 90 degrees about the origin. If we have x to the -1/2, that's the same as saying 1 over the square root of x. Notice that you're still going through 1, 1, but you're going to an asymptote at x equals 0, going up to positive infinity. And as you go to additional roots, you continue to be anchored at 1, 1. You still have asymptotes along the x and the y axes, and the additional roots simply stretch the graph a little bit one way or another. Now, I said that when we talked about shifts in scaling for linear graphs, it actually applies very nicely to nonlinear graphs. If you add a constant to a nonlinear graph, it simply shifts the graph up or down. If you multiply the graph by a constant, it will stretch one of the axes to rescale it. If you multiply it by -1, it's going to reflect the graph around the y-axis. If you just add a constant to the x value, that will shift your graph left or right. And if you multiply the x by -1, it's going to reflect the graph about the y-axis. So here we can see for the graph of y equals x cubed, adding the constant plus 2 simply shifts it up by 2 units. If we take x cubed and we add the value 2 to it, that will simply shift the graph to the left. But notice that when we add the 2, we're not adding it to the entire function, we're adding it to the variable x. Here, if we put a coefficient in front of the x cubed, basically we are stretching the graph a little bit. So you can see that multiplying it by 2 will stretch the graph, will squeeze the graph in, while multiplying it by 1/2 squeezes the graph out. For graphs of logarithmic functions, remember that we have all of the pure logarithms are going to go through the point 1, 0. So the red line here is just your standard natural log function going out to positive infinity as x approaches, or sorry, going out to negative infinity as x approaches 0, and gradually sloping upwards as x increases. The graph of negative logarithm of x is the same graph, just rotated across the x-axis. So if you think about there being a mirror at the x-axis, the green line is the rotation of that red line about the x-axis. If you multiply a logarithm, the x in the logarithm by a constant, then your graph will be stretched in such a way that it is no longer going through the point 1, 0. In contrast, if you multiply it by a coefficient in front of the logarithm, it's simply going to stretch the graph but remain anchored at that point 1, 0. If you have a negative x, so now you're multiplying x by -1, all that's happening to your graphs here is that they are rotating across the across the y-axis. So in the previous slide, we had the same exact picture, just on the right, flipped across to the right-hand side. So now that we've talked about logarithms, we'll talk about the inverse function exponents. Notice that the pictures here are basically the same as the pictures we were seeing before, but turned 90 degrees about the origin. So instead of having our graphs go through the point 1, 0, they are going through the point 0, 1, because any value raised to the exponent 0 will be equal to 1. So here we see 5 to the x. We have a negative asymptote along the x-axis. It goes up, curves up through the point 0, 1, and then grows rather rapidly. If we multiply the entire function by -1, it just rotates across the x-axis. If we multiply x by a coefficient, what we see is kind of like what we saw before. It stretches, the graph becomes more extreme between the asymptote and the anchor point 0, 1. It stretches inward, and then the tail for the positive x values is simply going up more quickly. And if you think about it, that makes sense. For positive values of x, 5 to the 2x should rise more rapidly than 5 to the x. Notice that just like before, when we multiply x by -1, what it does is it rotates the graph around the y-axis. When you think about actually having to create a graph, so not just identify the graph of a particular function, but to actually create the graph, there are a few things you always want to do. You should start off by setting x equal to 0, finding the y-intercept, set y equal to 0, find the x-intercept, find any inflection points, and we'll talk about that more when later in this class, and identify for the form of the graph any of those points like 0, 1, or 1, 0 that all of the graphs should pass through. And then finally, you're going to pick a few x values between the key points that you identified before and compute the corresponding y values. And you apply your knowledge of the functional form to fill in the line segments in between those points. So the very last topic for graphing is just a little bit about graphing parabolas. So parabolas are second-order polynomials, as you see here. And we know that the vertex, which is the point where the parabola switches directions, is going to be located at the x value of -b/2a. You're welcome to memorize that formula, but since we're going to be talking about calculus in a few weeks anyways, I think it's worth pointing something out to you. So what happens when a parabola switches directions is basically the slope of the parabola itself, or the derivative at that point, is equal to 0. So this vertex equation actually comes by taking the first derivative of your equation for the parabola. So in this case, if you take the first derivative, the derivative of the first term is 2ax, the derivative of the second term is b, and the derivative of the third term is 0. So you have 2ax plus b, and we know that at the vertex that will be equal to 0. So you rearrange the equation. You subtract b from both sides, you divide by 2a, you get that the first derivative is equal to 0 when x is equal to -b/2a. Similarly, if you're interested in knowing whether the parabola opens up or opens down, you look at the coefficient a, and if that coefficient on x squared is positive, then you know that the parabola opens upwards, is a cup shape. If the value of a is negative, is less than 0, you know that it opens downwards. That's basically the same as saying that the second derivative is positive or negative. And so you may hear your professors talk about knowing that the parabola opens up or down based on the fact that the second derivative is positive or the second derivative is negative. So in this case, the second derivative would be 2a. When you're ready to actually graph the parabola, you would plug in x equals 0 to find the y-intercept, plug in y equals 0 to find the x-intercept, or use any of the root methods to find the roots. Plot those points, plot the vertex, and use your knowledge of the second derivative, or that coefficient a, to decide whether the parabola should open up or open down. And with that, we are done with